Welcome everyone, I'm Dr. Chem, and in today's explainer, we're embarking on a cinematic journey into something truly awe-inspiring. Picture this, sweeping drone shots of massive wind turbines across coastlines and green fields at sunrise. It's absolutely breathtaking, right? But how does it actually work? Today, we're going to demystify exactly how we take something completely invisible, the wind, and engineer it to generate massive amounts of electricity. We'll start right here in the lab with some hands-on microscale engineering, and then scale those exact same concepts all the way up to those towering megawatt-producing giants.
Okay, let's take a really quick look at the blueprint for today. We'll be covering harnessing kinetic energy, the anatomy of a turbine, blade design and materials, how to measure our electrical output, and finally, scaling up wind power.
So, let's jump right into Section 1, Harnessing Kinetic Energy.
Imagine for a second that a 250-pound linebacker is running directly at you at top speed. You're going to move out of the way, right? Of course you are, because intuitively you know that moving mass possesses a terrifying amount of kinetic energy. You definitely do not want to be on the receiving end of it. Well, believe it or not, wind works exactly the same way. Air actually has mass, and when it moves at high velocity, it contains an incredible amount of kinetic energy. Our goal here is to build a machine capable of catching that charging linebacker.
Now, to catch all that energy, engineers basically use two aerodynamic approaches. First, you've got vertical axis turbines. These operate mostly on drag, meaning one side just catches more wind resistance than the other, which pushes the shaft to spin. But modern horizontal axis turbines, they use something much more efficient, aerodynamic lift. Shaped exactly like airplane wings, these blades use lift forces to actually spin the rotor even faster than the wind itself is blowing.
Moving right along to Section 2, Anatomy of a Turbine.
The absolute most critical component you need to know about is the nacelle. Whether we're looking at a small classroom model or looking at CGI revealing the internal operations of a grid-connected behemoth, the nacelle is the heart of the machine. It sits right at the top of the tower, and it houses the generator, the gearboxes, and all the crucial equipment that magically converts rotational motion into usable electricity.
To really understand this, let's shrink things down and look at the mechanics on a micro scale right here in the lab with a DIY turbine build. On the left, we've got a small nacelle housing a simple DC motor acting as our generator, with positive and negative wires feeding out the back. Then, on the right, you can see those wires routed down through an aluminum tower and into a sturdy wooden base. And here's the crazy part. This is the exact same fundamental architecture used in massive commercial turbines, just scaled down so we can literally hold it in our hands.
Building one of these functional miniature turbines is actually surprisingly accessible. You just feed your wires down the tower, secure the nacelle post, route your electrical connections through the base, and then press your blades onto the generator shaft. It's a pretty straightforward mechanical assembly for sure, but it perfectly models how structural support and mechanical energy capture work together.
All right, let's hit Section 3, Blade Design and Materials.
For this part, I want you to step into the shoes of an aerodynamic engineer for a minute. To maximize power, you've got to optimize several variables. Like if your blades are too heavy or too wide at the tips, you create drag, which totally kills your rotation speed. The real secret is finding the perfect pitch. Setting the blades completely flat or at just a slight 0 to 5 degree angle changes the game. Even better, engineers twist the blades. They keep them flat near the tip but twist them 10 to 20 degrees near the root to handle the different travel speeds all along the blade's length. It's brilliant.
But hey, optimization isn't just about shape, right? It's about material science. Fiberglass is basically the workhorse of the industry. It's affordable, it resists corrosion, and it has an amazing strength-to-weight ratio. Then you have carbon fiber, which is even stronger and lighter, but it's super expensive, so engineers use it really selectively for reinforcement. And holding all these composite fibers together, that's epoxy resin. It acts as the binding agent that provides the intense structural integrity needed to survive literal gale force winds.
And the coolest part is you can practically test these theories yourself. Here we have some custom-designed corrugated blades, which, is basically high-tech cardboard, attached to a 12-hole crimping hub. This hub lets you manually change the pitch and swap out different materials to physically see how drag and lift affect your RPM under a fan. It's an incredibly elegant, affordable way to prototype before we build the big stuff.
Which brings us perfectly into Section 4, Measuring Electrical Output.
Because once those custom blades are spinning, we need to know how to actually quantify the power we're producing. We measure two specific things here. First is voltage. Think of this as the electrical pressure pushing the energy. It naturally increases the faster our generator spins. The second is current, measured in amperes. This is the actual rate of electron flow through our circuit, and it depends heavily on the torque our blades are generating.
So let's look at a real testing circuit on a digital display. We use multimeters to measure both our voltage and our current, but check out that crucial addition right in the middle of the circuit, a resistor. See, wind is naturally inconsistent, which means the voltage fluctuates wildly. By adding a 50 or 100 ohm resistor, we're basically placing a load on the generator, forcing it to do actual work. It's really the only way to get a realistic measurement of our turbine's true power output.
And here is an absolutely brilliant engineering trick when it comes to those internal generator coils. When you generate alternating current inside the nacelle by passing magnets over fine wire, the way you wire them matters immensely. If you connect 4 coils together in a series circuit instead of parallel, boom, you get an immediate quadrupling of the voltage. It is a highly efficient design principle, and it's used all the way up to the biggest commercial turbines.
Now, for our final section, scaling up wind power.
Okay. Everything we've talked about so far is governed by one beautiful mathematical formula, the power in the wind equation. Power equals 1/2 the air density times pi r squared times the wind velocity cubed. So what does this actually mean for us? Well, it means power output increases exponentially. If the wind blows just a tiny bit faster, the power cubes. And if we make our blades longer, increasing that r for radius, the power squares. That pi r squared part of the equation, that represents what engineers call the swept area. It's the massive circle inscribed by the tips of the spinning blades. Because we can't change air density, and we certainly can't control the weather to increase wind speed, expanding this swept area is the primary lever engineers pull to exponentially increase a wind farm's energy capture. When we look at that scaling in practice, the progression is just staggering. We start from a standard 1.8-meter human up to a classic water pumper, then to a residential scale turbine at 24 meters tall, and finally, a towering 80-meter utility-scale giant. Yet the fundamental physics of lift, drag, coils, and magnets, they remain exactly the same across every single one of these machines. To put some real numbers to that scale, a residential turbine with just a 7-meter rotor diameter, which the industry still considers small by the way, can produce 10,000 watts, or 10 kilowatts, in a 25-mile-per-hour wind. That is enough generated electricity to power an entire house, completely off the grid. But when we scale up to that 80-meter utility giant, the numbers get absolutely mind-blowing. Thanks to that exponential power equation, a single utility turbine can generate 1,500,000 watts, or 1.5 megawatts. That is enough clean electricity to power roughly 400 American homes simultaneously, all from a single generator spinning up there in the sky. Which leaves us with this final thought. We started right here inside the lab with tiny DC motors and DIY nacelles and scaled all the way up to fiberglass giants powering hundreds of homes. With current research pushing into ultra-lightweight nanomaterials and advanced biocomposites, engineers are figuring out how to build blades even longer without adding any extra drag. So just how massive and how powerful will tomorrow's swept areas become? The blueprint is there, and the sky is quite literally the limit. Thank you so much for joining me on this explainer. Keep learning, and I'll catch you on the next one.